Aloha. Welcome to Live from NOIRLab at Gemini. My name is Jamika Marshall. I am an outreach assistant here at the International Gemini Observatory, a program of NSF's NOIRLab here in beautiful Hilo, Hawaii. Before introducing today's special staff guest scientist, I'd like to review a few housekeeping items. Those of you joining us, all of you on our YouTube channel, thank you again for being here. Please type your questions into the YouTube live chat window at any time during today's presentation. Our moderator, outreach assistant Alyssa Leinani Grace, will post or read the questions for myself and our science guest to answer today. So please don't hesitate to add in any questions or comments throughout the presentation. We will have questions that Alyssa will point out throughout the presentation as well as at the end of the presentation. So no worries if you don't have a question at the top of your mind yet, you have plenty of time to add it into the chat. Also, please be aware that there will be about a 30-second delay or lag time for the live stream. So we very much appreciate your patience and your understanding. So today we do have a special guest with us. Our special staff guest scientist is Andy Adamson. Andy is the Associate Director for the Hawaii site at the International Gemini Observatory. As an astronomer, he has studied interstellar gas and dust, mostly using the techniques of infrared spectroscopy and polarimetry. He's worked in observatory operations on Mauna Kea since 1998, first at the UK Infrared Telescope and now at Gemini. Thank you, Andy. We look forward to having you join us in just a moment. But first, a little bit of background about our Gemini Observatory. So, the Gemini Observatory is composed of twin telescopes. Each has a mirror of 8.1 meters or about 26.5 feet. Now, Gemini South is located on North Chile's Cerro Pochon, while Gemini North is located on Mauna Kea here on the island of Hawaii. With a telescope in each hemisphere, the observatory can view objects throughout the entire night sky. Now, Gemini South here is located again on Chile Cerro Pachon, and we have here just a stunning view, Gemini North, again, located here at the summit of Mauna Kea, you can see the dome is open and is very active. We see the beautiful sky above us moving, and the dome is turning as operations continue. Now, Andy, question. As the dome opened, we saw that it seems to have these very large openings or vents as part of the dome. Now, other telescopes, other observatories I've been to open in a different way where the dome kind of opens flat and the telescope is exposed. So can you explain why Gemini has such a unique setup?
Yeah, I can explain that. So most telescopes of this sort of size have a slit which the telescope can observe through. Gemini has these side vents which allow air to flow through very, very freely. This reduces the seeing that we see due to warmth in the dome escaping through the dome slit. And it's been known for quite a while that this would help. Gemini takes it somewhat to extremes, I think, but it's very effective, yeah.
Yes, thank you, thank you. So just really quickly, last month in our press release, an April press release, there was a very interesting story caught my attention. I'd like to share it with our audience here and then get a bit of feedback from you on it if we can, Andy. In this April press release, astronomers using the International Gemini Observatory imaged a very small object in orbit around the Earth. Now, this object was thought to just, to be very small, and we weren't actually sure if this was a natural object or a human-made object. Now, it was discovered orbiting in February, and it was given a designation of 2020 CD3 by the International Astronomical Union's Minor Planet Center. Now, according to the press release, if it's of natural origin, such as an asteroid, then this would only be the second known rocky satellite of the Earth ever discovered in space, other than our moon. The other body, discovered in 2006, has since been ejected out of Earth's orbit. Andy, can you give us an update on the status of this mini moon?
Before Andy talks to us about the amazing mini moon, could we please put up the slide so that we can see the picture of the moon?
Apologize. Thank you. Thank you, Alyssa.
Yeah, so I can say a little bit about this. The picture you're seeing, the mini moon is the little dot in the middle, which doesn't look very spectacular or anything, but it was really moving quite fast when this image was taken. And so all of the stars in the image are trailed out, and you can see that we took red, blue, and sort of yellowy green exposures to get an idea of the color of the mini moon, and tried to distinguish whether it was a rock or just an old rocket casing, for example, which there are plenty of those around. Turns out it's a rock, and it's now, as you said, left Earth's orbit. It may come back in the future, but for now it's gone, and we had one fleeting chance to figure out what it was. Later on, when we talk a little bit more about Rubin Observatory, I'll point out that, if I remember, I'll point out that the Rubin is expected to find quite a lot of these. So this is a unique, almost unique object right now, but there should be quite a lot of them, and we expect to discover them later.
Excellent. Thank you so much, Andy. And now we will move on to Andy's main presentation. Let me change here so we can see Andy. So Andy, I know that you're going to be talking to us about telescope operations and multi-messenger astronomy. So take it away.
Hey, I will. Are you seeing my screen? Are you seeing my picture? Okay, jolly good. So
Take it away. Actually, we do have one question on our YouTube channel regarding the mini moon. It's from Jerry Brower, and he wants to know, how fast are each of the color pictures taken, i.e. time between changing filter or whatever?
I can't tell you the exact numbers for this one, but they were fairly short exposures, so in the minutes rather than hours. Right? And so it took a while to get the image, but it's not like taking a snapshot. So yes, thanks, Jerry. And if you want to know the exact details, probably Andre Nicolau could tell you.
We also have a press release about that mini moon photo on our National Astro website, so everyone go check that out. On to you, Andy.
Okay. So just another look at the telescope, because there are some things that I'd like to highlight about it, which make it uniquely flexible. The fact that it looks bent is just an optical illusion. Because of the camera, you need a fairly wide angle lens to get the entire telescope in. It just about fits in the enclosure, as you can see. And as Jamika said earlier, the primary mirror there is about 26 feet across. And you can see down here on the floor, there's a person for scale. The thing that makes Gemini really flexible is that it works at both visible and infrared wavelengths. You can notice that the structure up at the top here, which holds up the secondary mirror, is actually very flimsy looking, and that's a sort of characteristic of telescopes that work at infrared wavelengths. We don't want too much material in the beam that our detectors at the bottom of the telescope would see. So that's why it looks that way. So if oops, let me see. So I should say a bit about the infrared, because having just discussed why we want to be visible as well as infrared. There are many reasons, but I'll highlight one. You're all familiar with the Big Bang, beginning of the universe as we know it. And you often see it represented this way. And it bugs me, because you could never have seen it this way, because the Big Bang happened everywhere. So in fact, if you were there around the time of the Big Bang, what you'd be seeing is this in all directions. It wouldn't be white light, it would be gamma rays. But nonetheless, it would be all around you, and there would be no seeing it from the outside, because the Big Bang happened everywhere. So the Big Bang sort of then expands and cools. Eventually it becomes transparent, and you start to see stars forming, and then galaxies forming. And if you look back far enough now, we see early galaxies indeed. So this is a picture from the Hubble Space Telescope, and the universe looks more or less the same in all directions. So you'd see this, something like this, in whichever direction the sky you looked at. All of these are very early galaxies. They're a long way away, and they're very, very redshifted by the expansion of the universe, and therefore we need infrared light to detect them. So just a quick note about the infrared. We've known about the infrared for a couple hundred years, I guess. This is William Herschel, who actually discovered the infrared, and you can see his telescope out the window there. But here he's got a prism up in his window, and he's expanding sunlight up into a spectrum. And being a good scientist, he's trying to measure the temperature of the light. And he's got 3 thermometers, because you need more than one to do this properly. And he moves them back and forwards between the different colors of light to see what the heating effect is. Just pure curiosity research. So he does that. He finds that red light produces a greater heating effect than blue light does. And then he does something that you might not have thought, which is, okay, what happens if we go past red light? And he finds that there's something there. So he finds that the heating effect further out than red is actually greater. So that's the discovery that there's something beyond the visible spectrum that we can see. And it's the first ever observation of infrared light, happens to be from the sun. So that's the sort of light that we use a lot at Gemini, particularly for things in the distant universe where the redshift is extreme, but also for things like star formation, where there's a lot of dust, which obscures the visible light, but doesn't obscure the infrared. So that's why our telescope looks the way it does. This is it seen from above. And this is a quick picture of the mirror, just to give you an idea of the scale. That's someone inspecting the surface of the mirror after a coating. We coat this every 5 years or so to give ourselves really good reflectivity. At the other end, this is our instrument cluster. I'll point them out. This is an instrument, and here's one. And we can switch between those instruments really quickly at night. So if something exciting happens and we need to switch to a different instrument, like moving from the visible spectrometer to an infrared one, then we can do that in 5 minutes and be on to the target and get science. So those are things that make Gemini really flexible. And they've certainly contributed to the future that Gemini has in multi-messenger astronomy and the time domain.
Okay, so we have a couple more questions, Andy, for you from our YouTube chat. Jose wants to know if the detection of the mini moon was while performing an observation or other tasks.
If I understand that right, it was detected by some other telescope. I can't remember exactly which one. And then somebody sent us a proposal very quickly to observe it before it was lost. Recognized that it was a faint object that was going to get fainter, and so they very quickly wrote an observing proposal, sent it to Gemini, and we then observed it. It was I think it was on a Sunday, and the proposal was worked up during the day, and the observing program was worked up in the afternoon, and then we observed it that night.
So I guess
Andy,
that observation really highlights how quickly Gemini can get a turnaround on these sorts of projects.
Yeah, and that's just the tip of the iceberg. Later on, by 2023, we'll be doing an awful lot of this. We'll come to that later.
Andy, I did find that detail on where we got the original image. It says in the press release that this was from the Catalina Sky Survey, which is operating out of the University of Hawaii's University of Arizona's Lunar and Planetary Laboratory in Tucson, Arizona.
That's right, and they look for this sort of thing. That's what they do. They look for near-Earth objects that may cause us a problem.
Okay, one more question from our YouTube chat. Stargazer Girl wants to know, how is the mirror recoded and how often?
So it's recoded every 5 years or so. And I say or so because we're hoping to coat it this year, and the current virus may get in the way of that. And it's coated with multiple layers. We put it in an enormous vacuum chamber that looks like a UFO, and we pump that down to a hard vacuum, and then we sputter metals onto the surface using what's called a magnetron. And that produces layers, and we have 3 of them, and the key one is silver, because silver has really good reflectivity. It reflects a lot of light all the way out into the infrared. And so it's a unique coating to Gemini, and it gives us that really good infrared performance.
Thank you so much, Alyssa. Andy, we're getting into a very interesting part of your presentation, multi-messenger and time domain astronomy. Now, this is a very new and exciting field of astronomy. First, can you tell us exactly what is multi-messenger and time domain astronomy? What are those referring to?
Okay, I'll do the second one first. Time domain isn't that new. I mean, we've known that things change in the sky for ages, right? There have been many, many variable stars that have been studied, and that is time domain astronomy. What's changed is that we now have other ways of detecting some of the more violent things that happen in the universe, and that's where the multi-messenger astronomy comes in. And by messengers, we just mean things that are, well, light is a messenger, for example. If a supernova goes off, we see it in light. But now, with advances in technology over the last few decades, we have other ways of detecting these things as well, some of which are pretty much unique. So I'll go on and talk about some of those. The first one is gravitational waves, which we first detected only a couple of years ago, 3 years ago. And they're detected with things that look like this. This is a picture of the Virgo gravitational wave detector, which is near Pisa in Italy. In fact, if you went off the left arm of this interferometer and headed off for another few miles, you'd get to Pisa Airport. There are 2 more like this, slightly bigger in the US, one in Louisiana and one in Washington State, and they're called LIGO. So this combination of LIGO and Virgo is enough to tell us where gravitational waves come from. So what this LIGO, what Virgo and LIGO both do, is to measure the length of this, and the length of that, and compare them. And so these tunnels are like a few kilometers long, and their job is simply to measure their own length, or the difference between them. Why is that useful? Because when a gravitational wave from some violent event in the universe comes through the Earth, it stretches everything, including the arms of this interferometer. And it doesn't stretch them by much. So this 2 kilometer or 3 kilometer arm probably changes in length by less than the width of an atomic nucleus. It's really, really tiny, and it's incredible that they can measure a change in the length of that small. But they do. And because we have 3 of these now around the world, we can get some sort of localization of where the event was up in the universe. So the first big result of this was a few years ago again. This is a merger of 2 black holes. And you can see the data from, this was entirely LIGO at that point, not Virgo. And you can see that the signal of the difference in length of the arms of the interferometer spins up, and then stops. And that's where the black hole is merged into a pond. Now, there are other predictions of violent events like that, like what if you have 2 neutron stars? And way back in the 1970s, there was some modeling done that suggested that neutron stars merging would produce lots of heavy elements. And here's a picture of the sort of thing you might expect. This is a model, I think. And what it shows with visible light over on the left here, and the rest of this is all infrared. So if you can get an infrared spectrum of a merging neutron star, you might be able to detect that there are differences in the spectrum, which depend on the amount of neodymium in the outflow from this event. And so this is called a kilonova, and one was detected a couple of years ago again. It always seems that the first event is the most exciting. This is a spectrum that was taken with Gemini South in Chile, and it looks a pretty good match to what you expect from an object that has generated a lot of neodymium. So again, visible light's over here on the left, and all of this is infrared, near infrared light. So neodymium's neat. I'll just show you a piece. It doesn't look that inspiring, but it has its properties. At the same time as generating neodymium, these objects, these kilonovas, these merging neutron stars also generate lots of gold and platinum, which is probably a bit more interesting to most people. But neodymium has its interesting properties too. On the Earth, there's about 120 million tons of it that can be mined, apparently. Looking down this list, the only member of the Gemini partnership that has this in any quantity is Brazil. But it's useful for making magnets, really useful for making magnets. And so if you've ever driven a Prius or an electric car, there are electric motors in there. And you're probably driving around with a couple of pounds of neodymium, at least half of which was made in a merging neutron star billions of years ago, before the Earth formed. And then just one little thing to close the loop here. The lasers that we use in gravitational wave detectors contain a bunch of neodymium. And so it's interesting to note that the detectors we're using to detect the creation of neodymium also use neodymium from one of those events more than 4,500 billion years ago. So, okay, neutrinos. Alyssa, I see you here. Is there a question?
Yes, we have 2 new questions from the YouTube chat. One goes back to talking about the mirror coding. And so Jerry Brower wants to know, what is the effect or consequences of delaying the recoding?
Over time, the amount of light that reflects from the mirror decreases. And when we first coat it, right immediately after the coating, in the infrared at about 1 micron of wavelength, so the left-hand side of those charts I was showing earlier, it reflects something like 98% or something of all of the light that hits the mirror. And then with time, that deteriorates, and so we're down a few percent at this point, and we'll be down another percent or two if we can't coat it this year. So that's the net effect. We're just a little slower to get to the same result.
Okay, and our next question from Stargazer Girl is, what size black hole can be detected using LIGO or Virgo?
Depends how close it is. Sorry, that's a cheat, because I don't really know the answer, but I believe that the merging black holes that I showed you the chart of were tens of times the mass of the sun, if I remember rightly. And when they merged, a few times the mass of the sun went into generating the gravitational waves that we now detect. But most of these big events are a long way away. They're in other galaxies, not our own. So yes, they're big black holes that we can detect. They have to be, otherwise they don't generate the signal.
Andy, if I may ask a question for clarity, you mentioned in talking about Virgo and LIGO that this element was created in a kilonova. Now, I'm sure many of our audience listeners are familiar with supernovae. Can you tell us what the difference is between a supernova and a kilonova?
So this is not my science, but I can say roughly. So a supernova is the explosion of a star which has run out of its nuclear fuel. So the center of the star then collapses because there's nothing holding it up anymore, and that creates a big bang, right? And then, and also it may create a neutron star. If it's a big enough supernova, it may create a black hole. But the kilonova is where you have two neutron stars in orbit around each other. And because of tidal friction and so on, eventually they're close enough and then they merge. And when they merge, a whole load of neutrons are liberated. And then those then go out to create elements that you couldn't actually create by processes inside the star. So, you know, and they're why we have a lot of the heavy elements that we have on the Earth.
Thank you so much, Andy.
And we have one more question from the chat. I think that this topic is very exciting for our viewers. So Dylan wants to know, what is the minimum density object which could create gravity waves that we can currently detect?
That's a good question. It depends how close it is. Same cheating answer. I think anything that's going to create, remember that the stresses involved in the changes of length in these interferometers are absolutely tiny, less than the size of the nucleus of an atom. So it has to be something really quite big to create a gravitational wave that's big enough to detect. And at the moment, we're detecting mergers of things at the sort of solar mass and bigger level. These neutron stars are fairly massive. They're also incredibly small. And so I think in terms of density, it's going to have to be at the moment something like the density of a neutron star or a black hole. Otherwise, we just wouldn't stand a chance to detect it. Interestingly enough, COVID-19 has resulted in great reduction in vibrations in the Earth because there's less transport going on. Unfortunately, at the same time, our gravitational wave detectors are closed down because people can't safely work. But it would be a nice quiet environment if they could.
So, Andy, as we move into neutrinos, I am very curious to know how neutral subatomic particles help us to understand more about our universe when it comes to multi-messenger astronomy.
Yeah, yes, it's interesting. So neutrinos are really, what's the word, slippery things. They don't interact with normal matter much at all. In fact, in the time it takes me to say neutrino, something like a million billion neutrinos have passed through me and through you and through everyone else who's watching, and those come from the sun. So if you're talking about this at night, they have come through the Earth and through you, and then they're off out into the rest of the universe. And right now, for me, the sun is up, therefore there's a whole lot of neutrinos coming from over there. Like I say, a million billion of them going through my head in the time it takes to say the word neutrino. So there are loads of them, but the fact is that they're really hard to detect. They go through things so easily that you can't pick them up. Right? So to do that, we have to do some clever stuff, and this is one of the coolest, I think, and that's all literally true because this is in Antarctica. This is called IceCube. This is not IceCube itself. This is the sort of office block sized thing that sits on top of IceCube. And this is a brilliant thing. I'll show you what it looks like underneath the ice, because that's where all of the actual detection goes on. So the building I was just showing you is this little office block thing at the top here. Below it, of course, there's snow layer, but then in Antarctica, the ice all the way down to the bedrock is actually pretty clear. And so what IceCube does is to have a load of optical detectors strung out on wires, and when a neutrino actually does manage to interact with a nucleus, it creates a shower of secondary particles, and that produces flashes of light, and those go through this array, and you can roughly tell where it came from in the sky. Now, this isn't like trivial because there's an awful lot of neutrinos from the sun, but they have clever ways of filtering them out and looking only for the ones that come from astronomical events outside of the solar system. So this is going on all the time. IceCube is fully operational. And just a note for the scale down here, here's the Eiffel Tower. This is a really large installation underneath the ice, and it's about a cubic mile or something like that. And the other reason that this works is because, you know, all of this ice gives the neutrinos something to interact with. And so this is what produces our neutrino detections from things like supernovae. And let me just move on to that. So this is an old supernova. Here's, you can see there's a suspicious looking arrow pointing at a star here. And this is in the Large Magellanic Cloud. Pretty inconspicuous star, and then back in 1987, that supernova went bang, and it produced this object which was incredibly bright. It was naked eye, and that was called supernova 1987A. I mean, we now have so many supernovae that you know, we don't have any shortage, but this one was quite special because it was quite close. And what neutrinos do, interestingly, is that when a supernova happens, they actually get out of the star sooner than the light does. So if a local supernova happened, you know, within, say, a few thousand parsecs of here, we would detect that as a bright pulse of neutrinos first. And then maybe 5 hours, 10 hours later, you'd see that star brighten up. So using neutrinos as a messenger, you can get to what is going to be a supernova even before you see it with visible light. So that's why it's exciting. Gamma rays. Yeah, so we've been flying satellites for quite a while, which detect gamma rays. You have to be above the atmosphere to do this. Here's over in the top right there, there's a pretty dramatic artist's impression of Swift, which is a gamma ray satellite, which tells us when a gamma ray burst happens. And these are very violent events akin to supernovae. And the rest of the picture here is my trash from my email, because although in normal times, Gemini would be responding to a lot of these and going off and observing them, right now we can't. But a lot of these events, you can see the numbers, they're either the detection of the event by Swift, or they are people following them up with small telescopes and large around the world. And like I say, at the moment, a lot of them are going off and Swift is detecting them, but we're not following them up. So that's the third messenger. And then fourth messenger is just regular old light, which is the stuff that we've been talking about previously, the sort of thing that these large telescopes on Mauna Kea and in Chile will detect. And the time domain itself is about to be revolutionized, something like 3 or 4 years from now, when the Rubin Observatory goes into operation. Elisa, I see you there. Is there a question?
Yes. So Sadie on YouTube chat wants to know, what is the closest black hole to Earth?
I believe it's about 1,000 parsecs away, or is it 1,000 light years, which would be 300 parsecs. And the reason I know that is because I saw a news article yesterday saying that one had just been detected that close. So that's just fortunate. That's still quite a long way away, right? The nearest star is hundreds of times closer than that. That's the nearest one to the Earth.
Okay, and Dylan wants to know, what are the quantum implications of detecting neutrinos from a supernova event before light?
I don't think there's any quantum implications. It's an expectation that we have. And the reason why it might be important is that if a local supernova goes off, if Betelgeuse decides to go supernova, it would be really useful to be able to say, okay, we know in a few hours this star is going to go supernova. We'll be able to observe it before it brightens, and we'd be able to see the entire event. I don't know if the nuclear physicists would learn too much from detecting the neutrinos sooner, because it's just a prediction that they will get out of the star sooner than light does. Maybe something that not really my expertise.
So, Andy, you mentioned that the Rubin Observatory is going to revolutionize time domain astronomy. Could you elaborate just a bit on that?
Yeah, sure. So this is a picture of the Rubin, named after Vera Rubin, who was one of the key observers of the fact that there was a problem with galaxy rotation curves and therefore there was dark matter. And this observatory is named for her. And it's designed to do one very special thing, which is basically a sky survey of the entire sky, more or less every night. I'm exaggerating slightly. And it's, at the moment, as I mentioned earlier, we'll get maybe a gamma ray burst a night or something like that. We get a few per night. In a few years' time, when the Rubin Observatory gets going, we'll get 10 million transients per night. And some of which will be solar system objects, they'll be moving things, others of which will be supernovae. It's going to revolutionize supernova studies. But the whole thing is designed to survey the sky so quickly that from night to night, you can compare these images with the reference image and detect everything that has changed. And that's a total game changer in this field. And of course, 10 million objects per night, one couldn't even consider observing all of those. So we're going to have to do clever things to filter them down to the ones that are really interesting, and then use the big telescopes to study those with spectroscopy and so on. So this is the sort of thing that we have in mind. This is the Rubin Observatory. I think this is a sketch from one of their articles. And by the way, Rubin itself is a member of the NOIRLab. And the idea is that this is data coming down from the sky into the Rubin Observatory. It has quite a large camera. Its CCD array is something like this big. I can get it in. And it sends the detections of all of these transient changing objects off into what's called a broker, which is a large computer system that filters them down and looks for the really interesting stuff. So, for example, if you're looking for supernovae, you might want to look in the fields of galaxies rather than separately out in the field. And so that's what these brokers will do. And then, having detected these objects, that will bring the numbers down considerably from 10 million. Then it's worth going off and saying, right, let's get some observations with small telescopes to try to narrow down the colors of these things, see if they're consistent with supernovae or with something else. And then at the far end of the chain are the large telescopes like the Blanco and the Geminis, which will do the more detailed spectroscopy on the most interesting ones. So, in a couple of years' time, we expect to be doing this, for at least a third of our time, and it's going to be a really productive phase of astronomy, I think.
So, Andy, if I may begin with a question that goes back to your last slide, you mentioned that the Rubin Observatory, once completed, could be tracking maybe 10,000 transients per night. Now, that's a lot of data.
I didn't say that. I said 10 million.
10 million, even more. Thank you. That's a lot of data. Now, maybe some of our audience members have heard of this too, that we're coming into the era of big data. Is this what's being referred to?
Yes, in astronomical terms, yes. I think we've been in the era of big data in astronomy for quite a while, I think, but this takes it to a different level altogether. Remember that the 10 million number is just the number of things that have changed. At the same time as scanning the sky every night looking for things that have changed, the Rubin Observatory is going to build up a really deep picture of the sky, and that's going to bring out galaxies that we didn't know about, things at very high redshifts and so on. So it really does produce a sort of sea change in the amount of data that we need to deal with. But some of the techniques we already know. People have been doing sky surveys since parts of the 20th century. And the way the data has been handled has sort of been revolutionized by the developments in computing and storage technology that have made it possible to really mine these data sets. And so a lot of the people who are early career astronomers now are getting very familiar with the tools that you need to mine data from large data sets like this.
Thanks, Andy. Our next question from the YouTube chat is from Stargazer Girl, and she wants to know what is the difference between gamma ray bursts and X-rays?
So it really is just the wavelength. I think in formal terms, gamma rays are more to do with nuclear reactions, and X-rays are more to do with standard ways of generating light. But in terms of the gamma ray bursts, it's the energy of the photons involved. So in other words, it's the wavelength and the frequency of them. The gamma rays are slightly harder. And so now these things are not easy to detect. Because they're gamma rays, they go through stuff. And so actually picking them up is a bit of a trick. In X-rays, we have ways to image the sky. So there are telescopes that have flown in the past and still flying, which can do images of the sky in X-rays. But gamma rays, because we can pick up roughly where it is have to go to the telescopes to figure out exactly where it is.
One more question, Andy, going back to gravitational waves. Now, how long had astronomers been looking for gravitational waves before they were actually detected?
I believe many decades, probably going back to the, I've struggled with my history here, but I think 1950s or something, there were people working in labs with much more primitive means of trying to pick things up, and much smaller than we're using now. But I think initially they didn't really know what to expect in terms of the stresses that would be induced by real gravitational waves. Or perhaps they were being optimistic. And then through the 70s, 80s, 90s, we got progressively closer to being able to detect these waves by building larger and larger interferometers and more clever the way we allow the light to interfere. So at the moment, and then by 2017 or so, we were actually ready to detect them for real. And that seems to have happened just because of LIGO. And the previous experiments weren't quite big enough.
Okay, one more question from the chat. Can Gemini support Rubin Observatory data with follow-ups?
Well, that's our intention, yes. In this picture that I'm showing, this is one of the Gemini telescopes. And because we have two, one in Chile and one on Mauna Kea in Hawaii, we're actually able to support Rubin Observatory follow-ups in two ways. Usually we refer to Gemini North and Gemini South as exactly that, North and South. In fact, when it comes to Rubin Observatory discoveries, you might think of them as Gemini West and Gemini East, because an event that is detected by the Rubin Observatory, which is in Chile, by the way, right next door to Gemini South, we can start observing that event with Gemini South, or Gemini East, as I said, and then take advantage of the longitude difference to carry on observing that object with Gemini North. And some of these things evolve so quickly that it's worth doing that. So yeah, Gemini does intend to be involved in following up Rubin Observatory, as do many of the other NOIRLab facilities.
Thanks, Andy. Another question from the chat from Jose. Could you explain what the relation between LIGO observations and EHT would be?
Yeah, there isn't really. So LIGO is looking for gravitational waves from, typically from mergers of black holes, and as we saw, neutron stars. I think that the Event Horizon Telescope is really trying to look at the detailed structure around the black hole itself. And so, as you know, they have had success with the black hole in 87, and there are probably more to come. But that's really to do with the details of how light is bent around the black hole and so on, and looking for the shadow of the event horizon, than it is to do with violent events like mergers of black holes. Remember when it took them a long time to build up enough data to get the image of Ehi, the black hole in the center of 87. So it's not something that can be used for quick observations of transient things that go bang.
Thank you so much, Andy. Again, Our special staff guest scientist today was Andy Adamson, the Associate Director for Hawaii Site at the International Gemini Observatory. Andy, I will let you have the last word. Can you tell us your hopes for what to expect from multi-messenger and time domain astronomy in the near future?
Yeah, it's that we don't know what to expect. If we are involved in discovering something that no one had expected, that's going to be fantastic. So I look forward to that. There are going to be things that no one expected out of this.
Thank you so much, Andy. And thank you, our YouTube Live audience, for joining us. We hope to see you again next week, right here on Wednesday at 1 p.m. HST. Aloha.